So now we're going to look at more examples in which we have substitution with an alcohol as the starting material. Keeping in mind alcohols are not good leaving groups, so we need to convert them to leaving groups before we do substitution. Two ways to do that would be making them into water by protonating them in acidic conditions, or the other way is turning them into a good leaving group like a tosylate or mesylate. And so we're going to look at a few of those examples. The first example, we're going to add tosyl chloride, which is toluene sulfonyl chloride, which looks like this. Then we have our benzene ring, it's a toluene, so we have a methyl group. This is TSCl. This right here is going to replace our hydrogen, making the oxygen a good leaving group. And the way it does it is via kind of an SN1 like process or SN2 like process. Our alcohol is going to add to the sulfur, kicking out the chlorine. And what we get is this. Now, keeping in mind, we did not interfere with this carbon, so the stereochemistry is not going to change. It's still going to be a wedge. Now we have our sulfur, double bond, oxygens. We have our benzene ring. Let me redraw that a little better. And this is an excellent leaving group. But before we do anything else, the pyridine there, its purpose is to remove the hydrogen, and what we get is our intermediate. Now you can abbreviate that whole piece as OTS, where this right here is the TS piece. This is a good leaving group. Notice we did not interfere with the stereochemistry of the carbon. We just replaced the hydrogen with a TS. You don't have to show the mechanism when they just want the product. I'm doing this just to show you why we get what we get. So now we have a good leaving group. It is secondary. We can potentially do SN1 or SN2 for our substitution because it is secondary. So if it did an SN2, what would happen is we would get backside attack, inversion of stereochemistry. Essentially the bromine would add, kicking out the tosylate, and get a dash. However, if this underwent an SN1 mechanism, we would form a carbocation, and then the bromine could add as either a wedge or a dash. And you'd get a racemic mixture of both. For this, I could see it going either way depending on the solvent used. So I'm going to show you that yes, you would either get the SN2 specific stereochemistry, or you get the SN1 mechanism, which is a mixture of the R and the S. It would be a racemic mixture in equal parts, 50-50 mixture. So now we're going to look at the next example. So again, let me just put that back in there. Bromine. This would be the SN2, and then the mixture would be the SN1. For the next one, same thing. We have that same starting material, but instead of making the alcohol a leading group that's a tosylate, we're going to protonate it, making it water. And what we would get is something like this. Again, it does not interfere with that stereochemistry. We did not interfere with the carbon. We just added a hydrogen to the oxygen. And one of two things could happen. The bromine could add SN2, which would invert the stereochemistry. Or we can form our carbocation, which is planar, and the bromine could add to the dash side or the wedge side. These would be the products of the SN1. Next, we're adding HI. Again, we're not going to draw everything out now, but the hydrogen is going to add to the oxygen, protonating it because we have an acid, hydroiodic acid. Because it is a tertiary alkyl halide, we will only do the SN1. we will lose water, form a carbocation, and then our iodine would add. This is not a chiral center, even though it was drawn with a dash and a wedge. It's just to somewhat throw you off. The iodine would add. You don't have to show dashes and wedges because that's not a chiral center. On the top right, same thing. We have an alcohol. We have an acid. We're going to protonate that alcohol, making it a good leaving group. If we did an SN2 mechanism, because it is secondary, we could do SN2. We'd put the bromine as a dash. If we did SN1, we would have loss of a leaving group, which would form a carbocation here, but then that's a secondary carbocation. We can shift a hydride to make the tertiary carbocation, and then our bromine would add up here. That's no longer a chiral center up there, so we don't have to show dashes and wedges. So this would be the SN2, this would be the SN1 product. The next example, again, that TSCl is going to convert that alcohol to the tosylate. It is a tertiary leaving group, so we're going to do SN1, kick out the leaving group, form our carbocation, and then our bromine will add. It is not a chiral center. We don't have to show dashes and wedges, just put the bromine on there. And for the last one, again, we have an alcohol, and we're adding NaI. Nothing's going to happen here, because remember, an alcohol is not a good leaving group. In adding sodium iodide, you just have the nucleophile there. It's not going to kick out the oxygen, because the oxygen is not a good leaving group when it's an alcohol. You would need to protonate it first. In order to do this, you would need to use something like HI, so that we could protonate the oxygen, make it a good leaving group, and then add the iodine. But if we just try to add I- as is, with no leaving group present, nothing would happen. The other possibility was we could have added first, we could have done TSCl with pyridine to make the tosylate, then we could have added our sodium iodide, and that would give us a product. But just adding a nucleophile to an alcohol is not going to do anything. That's going to be no reaction.